So this is good morning, students. In this presentations, we are going to see about logic gates. So this is the part of unit in optics and electricity. So here, what does mean by logic gates? So this can be explained as the building blocks that is used to create digital circuits that are called as logic gates. The combination of transistors that performs binary logic. Binary logic means 0 or 1. So next is that here there are three elementary logic gates are available and other range of symbol gates are also available. Each gate has its own logical symbol and allows complex functions. It will be represented by a logic diagram. So here the function of each gate is represented by a truth table or Boolean notation. So by using Boolean notation, so we can represent that function of each gate. Next is that so that output and input of logic gates can be explained by two levels. One is that high or low. Next one true or false. Next is off. Then that high on one same meaning and also that low of zero that are having that same meaning. So next is that what is meant by logic. So here the logic in which the voltage levels represent logic 1 or logic 0. So that level logic may be, so here the level logic may be logic 1 or logic 0. The level logic can be also denoted by positive or negative. Positive logic means higher of two voltage levels represents the logic 1 and lower of the two voltage level represents the logic 0. Negative logic means one which the lower of two levels represents the logic 1. Then higher of the two voltage level represents the logic 0. So it is called as the negative logic. Then the gates are classified into different types. that are NOT gate, AND gate, OR gate, NAND gate, NOR gate, XOR gate, XNOR gate, and buffer gate. So first of all, we are going to see about NOT gate. Here, NOT gate accepts one input value and it produces one output value. Here, by definition, if the output for that NOT gate is 1 means the input value of that NOT gate is 0. So if input is 1, the output is equal to 0. Then NOT gate is sometimes refers to as inverter gate because it inverts that input value. Here, that Boolean expression for NOT gate is x equal to A inverse. That logic diagram symbol is denoted by like this way. Next is that this will be the truth table. If that input is 0, output is equal to 1. Next, if the input is 1, the output is equal to 0. By using transistor, this will be a NPN transistor. By using this transistor, the NOT gate has to be designed. So, here transistor, there are three terminals are there. This will be emitter, this will be a collector, and this is the base. So here the transistor is used for switching or amplification process. Due to that property only, we are using it as a switch for NOT gate operation. The transistor used for the design of NOT gate depends upon that transistor switching speed. Here, there are three modes of transistor operations will be there. One is that active, another one is saturation mode, another one is that cutoff mode. Out of all the three, we are using that saturation and cutoff mode for that NOT gate design. So here, with that base of transistor, one resistor is connected, and with that collector of transistor, one resistor has to be connected. So this will be that operation when A is equal to 0. When A is equal to 0 means that current is passed through that transistor resistor. Here we are getting that output as 1. Here the voltage applied can be less than 0.7. So this can be written as the emitter of the transistor can be written in terms of half mode. So if A is equal to 1, A is equal to 1 means that transistor. Here, that ground level is taken as on operation. Here, the voltage applied should be greater than 0.7. Next one is that AND gate. Here we are using two input signals. The two input signals are both 1, 0. Here we are getting only one output. That Boolean expression for AND gate is A dot B. Dot means here multiplication. That logic diagram symbol for AND gate is given here. From this AND gate truth table, when both the inputs are low, we are getting low output only, and if any one of that output is high, the output is low. So if you want to get the output is equal to 1, the both that input should be equal to 1. So that AND gate truth table. Next one is that we can realize that AND gate but by using diodes. Here we are using two diodes. That anode of that diode, that means negative end of the diode, is taken as inputs A and B. Then that positive end from that diode 1 is taken as that output. From that diode 1 resistor is connected, and it is connected to a battery, a positive voltage. So here how that gate is working. So here we are using that two diodes. So if A is equal to 0, if A is equal to 0, here that diode connected with that input 0 can be closed, and the current is passed through that corresponding diode and through the resistor, and thus the anode of the diode will be logic 0. Then if both that inputs are 1, the two diodes are reverse biased and no current is passed through the diode. So therefore the output is logic 1 because no voltage drop across the resistor R. Then here if one input as 1, one output input as 0, so that here that input connected with the diode 1 is reverse biased and diode 2 is forward biased, so that current can be passed through the diode 2. So we are getting that output is equal to 0. Likewise, then A is equal to 0, B is equal to 1. Same has to be followed. So next one is that OR gate. So here that OR gate is represented by the Boolean expression x equal to A plus B. Here, the logic diagram of OR gate is A, B. Here, this will be the logic diagram. The truth table is also explained here. So here, if one of the input is 1, we are getting the output 1. If both the input values are 0, the output value is equal to 0. This is the condition for that OR gate. So here that realization of OR gate is done by using diode. Here also we are using two diodes D1 and D2. From the end of the D1 diode, output has to be taken, and the two diodes are connected by their negative end, and it is connected to a resistor, and it is grounded. So here, if A is equal to 0 and B is equal to 0. So if logic 0 on that output, then both that inputs are 0. So in this case, the diodes do not conduct. So there is no current is passing through the resistor and no voltage across the terminals. As a result, the voltage at V output is same as that ground. So here, when A is equal to 0 and B is equal to 1, we are getting the output as 1. Here, the current will flow through one or both the outputs. If here, this will be current can be passed through one diode. So the current passed through the resistor, and this will causes that voltage across the terminals. Thereby, we are getting that logic 1. If both that inputs are 1, both the diodes conduct and the current is passing through the resistors, and this will causes that output voltage across the terminals. So here we are getting that output as logic 1. So these are that realization of OR gate by using diodes. So next is that and NOR gates. These are essentially the opposite of AND or OR gates. So they are called as universal gates. The Boolean expression of NAND gate is that x is equal to a into b dash. So here in that truth table, if both the outputs are 1, we are getting the output as 0. If both the inputs are 0 and any one of the input as 0, we are getting the output as 1. So that logic diagram symbol can be represented by using this symbol. Next, that Boolean expression for NOR gate is A plus B inverse. The logical diagram is denoted by like this way. In this truth table, so here, if both that inputs are 0, we are getting the output as 1. If any one of the input as 1, we are getting the output as 0. So this will be that conclusions from the truth table of NAND and NOR gates. So here, already as I told, these NOT and NAND gate are using as a universal gate. By using NAND and NOR gate, we can produce different kinds of gates. Here, this diagram, here NOT gate is NOT gate is formed using that NAND gate. So here they are taking only one NAND gate that inputs are combined together. It is taken as a one input. So here we are getting the output as y is equal to a dash. So this will be that output of NAND gate. Sorry, not gate. So next thing is that the AND gate is framed by using that NOT gate. So for that we are taking two NAND gates. First NAND gate, we are taking two inputs as A and B. The output of that first NAND gate is A dot B inverse. So next, that second NAND gate is taken after the first one. For that, that inputs are combined and the output of first NAND gate is taken as the input of the second NAND gate, and the output is taken from the second NAND gate. So here we are getting the output as y is equal to a dot b. So this will be the output of AND gate. So next one is that OR gate by using NAND gate. So here we are using three NAND gates. That first two NAND gates inputs are combined together, that will be taken as the input of that OR gate. Next is that output of the first one and the output of the second one is connected to the another NAND gate. So that will be taken here. So by using that De Morgan's theorem, we are getting the output as y is equal to a, a bar dot b bar the whole bar. That is the output. So by using De Morgan's theorem, that will be simplified as a double bar plus b double bar. So then y is equal to a double bar is equal to a, then b double bar is equal to b. So we are getting y is equal to a plus b. That will be that output of our gate. So here that NAND gate is produced by using NOR gate. So here also we are taking four NAND gates to produce the NOR gate. So first uh, two NAND gates inputs are combined together, that will be taken as the input for that NOR gate. Next is that output of first two NAND gates is taken as the input of the third NAND gate, and the third NAND gate output is taken as the input of that fourth NAND gate. So here that Y3, that output of the third NAND gate can be written as A bar dot B bar the whole bar. By using De Morgan's theorem, we can return as A plus B. Then the output of that third NAND gate is taken as the input of fourth NAND gate. So we are getting the output is equal to A plus B the whole bar. So here, next, the NOT gate have to be formed by using NOR gate. Here we are using only one NOR gate. So here, that input of NOR gate is combined together and taken as the input, and output is that y is equal to a bar, that is the output of that NOT gate. So next one is that OR gate by using that NOR gate. So here we are using two NOR gates. That input is taken from that first NOR gate. The output is of that NOR gate is that input of the second NOR gate. So here we are getting the output as y is equal to a plus b. So that is the output of OR gate. Likewise, OR gate is produced by using only NOR gate. The last one is that AND gate using NOR gate. So here we are using three NOR gates. That output of the third NOR gate is that output of AND gate. So we are getting the output as y is equal to a dot b. So likewise, NAND gate is produced by using NOR gate also. So here we are using four NOR gates to produce the NAND gate. So all that things we are using that only NAND and NOR gates. We can produce different types of gates, and that can be called as that universal gates. This is the reason behind that universal gates. Next one is that XOR gate. So this is in other terms is called as exclusive OR gate. That XOR gate produces 0 if two inputs are same and 1 otherwise. So here that Boolean expressions of XOR gate can be written as X equal to A plus B. So that is A exclusive B. Then next is that the logic diagram symbol is taken here. The truth table is given here. In this, if both that inputs are 0, we are getting that output 0. If both inputs are 1, we are also get that output as 0. If you want to get that output as 1, if any one of that input is equal to 1. So this is that case of XOR gate. That X NOR gate. Next one is that X NOR gate. So here the symbol of X NOT gate is given here. In this truth table of X NOT gate, if both that inputs are 1 or 0, we are getting the output as 1. If any one of the input is 1, we are getting the output as 0. So this will be that conclusions from that truth table of exclusive NOR gate. So next one is that buffer gate. What is meant by buffer gate means it returns the same output as same that of that input. So if input is equal to 0, the output is also equal to 0. Input 1 means output is also equal to 1. So it is called as buffer gauge. So by using gates, the digital logic circuit have to be framed. So this is called as that combinational logic circuits. The digital logic circuits whose inputs can be determined by logic function of current state input that are called as combinational logic circuits. So in this diagram, we are taking two AND gates. That is here that input of first NAND gate is shared by the second AND gate. Then the output is given to a OR gate. Then the output of that OR gate is taken. So here there will be a combination of uh, and OR gates are there. So it is called as combinational circuits. So here that combinational circuits are classified into different types. Here, as soon as that input of that combinational circuits are changed, the information about that previous inputs is lost. So here we are taking that conclusion as combinational logical circuits have no memory. So here these are that some of examples of combinational circuits. These are adder, subtractor, decoder, encoder, multiplexer, demultiplexer. These are that examples of that combinational circuits. Next one is that sequential circuits. In this sequential circuits, combinational circuits also used. Here, the digital logic circuits whose output can be determined by using logic function of current state inputs and the past state inputs and also store that information. These are called as sequential logic circuits. So in this diagram, with that combinational logic circuit, there is one input and output is taken. That input is stored in that memory. So here we are using that positive feedback. Here that output can be taken as a logical clock signal. So here these are that some points about logic circuits. So that logic circuits have to be used in many places like orders, subtractors, multiplexers like that. So in this presentations, we saw about different types of gates how that outputs have to be taken, how it will be explained by using that truth table, and that NAND and NOR gate can be called as universal gates, how we can produce other type of gates by using NAND and NOR gates. So that reason only they are called as universal gates. By using logical gates, different types of combinational circuits and sequential circuits have to be trained. So here that combinational circuits don't have any memory. So we cannot store that data in that combinational circuits. But in sequential circuits, we can store that memory. So in that sequential circuits, we are taking that combinational logical circuit as one part. Here, the input and output is taken from the combinational logical circuits, and the input of that is stored as a memory in that sequential circuits. So it is having some memory. Here we are using that positive feedback. So these are the some points about logical circuits. This can be used in different places. So I hope this will be very useful for you to know about that logical circuits. Thank you.